So now that we've done some permutations, which is questions where the order matters, we're going to try a few where the order does not matter. And to try and tell the difference between those two scenarios, we're going to talk about these three individuals trying to run student council. So if Jim, Sam, and Sally are all interested in running the student council, how many different ways could we set that up? So if we were to do this in a way where order matters, we would have to assign these three people to distinct roles so that you could tell the difference if Jim was the president or if Jim was the vice president, for example. So we'll go with those two positions, president and vice president. So if we were to set this up like we did in the last video with permutations, I'd need a box for this particular row and a box for this particular role. And if there are only two positions, we'd ask ourselves, how many choices do I have for president? Well, there are three people here, so that's three choices for this one. And once you select your president, there are only two people left for vice president, which gives you a total of 6. If we were to do this in a way where the order doesn't matter, we'd have to find a way of arranging our student council so that there weren't different positions in the executive. Order doesn't matter. So I know at Grey Highlands, at least, that they do not have a president and a vice president of student council. They have two co-presidents. So both of those people have equal responsibilities and they have equal authority over everything. So it doesn't matter whether you're co-president number 1 or co-president number 2. You are simply considered a co-president. So if we were to do that, co-president, co-president, suddenly the order is irrelevant. Now, in order to figure out how to count these, I'm going to make the list of ones where order matters, and then we'll see what happens when I take that condition away. So if I were trying to select a president and a vice president, then my options could have been Jim and Sam, Jim and Sally, Sam and Jim, Sam and Sally, or Sally and Jim, Sally and Sam. So as expected, there are 6 different ways that they could play out. And if you're not convinced that Jim as president and Sam as vice president is different than Sam as president and Jim as vice president, if you just take a look south of the border, which as of right now has Donald Trump as president and Mike Pence as vice president. Now if you think about switching those two in their roles so that it was President Pence and Vice President Trump, the last 4 years would have been a very different scenario for that country. So there is a difference assigning these two people different roles, and our counting has had that show up, that there are 6 ways that you can make that happen. And if I go to this one, where the order doesn't matter, and I simply make them co-presidents, then this line here, where Jim is one co-president and Sam is the other, is no different than this row. So these are the same. And then this row here, where Jim and Sally are on the executive, that row is the same. And this row where it's Sam and Sally, they're the same. So it turns out that if order doesn't matter, there are only 3 different ways to do this. Jim and Sally, Jim and Sam, or Sam and Sally. Alright, so it would be nice to have a way to calculate this when we're doing counting instead of having to make a list. Because you can imagine, if I had 8 people in the running and 4 different positions, suddenly this list is going to get very long. And like the permutations questions, I don't want to have to do that in order to count my outcomes. So I'm just going to make a little space here. So there must be a way to get rid of the arrangements of the people we choose to keep, because that is the issue here. This one imposes order on the candidates we select, and we're trying to get an answer that does not impose that order. So fortunately, there's a technique we've already used to eliminate arrangements, and I actually did it here. You maybe didn't realize, but let me write it out for you. This was a question where the order mattered, all of the objects were distinguishable, so I could tell each of these people apart, but I left some behind. So when we had questions like that in the last example, we took everyone that was available to us, and we divided out the arrangements of the people who got left behind. Now, unfortunately for the loser of this particular group, there's only one of them. So the one person I left behind, I needed to get rid of their shufflings. So 1 factorial is 1, which doesn't end up changing the answer when you divide by 1. But this shows us the structure that we're going to use. So down here, I still had 3 people running, and I still left 1 behind. But what's new this time is that the 2 that I kept, I need to discard their orderings. Well, if this discarded the orderings of the ones I left behind, then this must discard the orderings of the one that I keep. So in this particular example, 3 factorial will be 3 times 2 times 1, which is 6. 1 factorial is just 1. 2 factorial is 2. 2 times 1 is 2. And 6 divided by 2 is 3, which is the answer I was hoping to arrive at. So if you are going to be doing a question without order, the only thing that's changed here is that once you get rid of the permutations of the ones you leave behind, you also have to eliminate the permutations of the ones you keep. So to make a slightly more complicated example, this time we're going to let 8 students be interested in running the student council as a triumvirate. So not just 2 co-presidents, but 3 people operating with the same authority and the same responsibilities. So once I select my 3 out of 8, it doesn't matter which order I selected them in, because they all have the same position. So it's irrelevant whether you're the first person chosen for it, because the second person is just as capable or powerful as the first. So if we were to do this, having 8 people and choosing 3 means that there are 5 left out and 3 positions whose order needs to be eliminated. My marker is getting a little tired. Alright. So, if I were to take these 8 people, the first thing I'm going to do is shuffle all of them. There we go. So they're all shuffled. But because I've left 5 of them behind, I need to eliminate the shufflings of those 5 people. And because the 3 positions are identical, and that the shufflings of my chosen 3 within those positions is irrelevant, I need to eliminate those shufflings as well. So, if I grab a calculator and I try 8 factorial, I get 40,320. And if I do 5 factorial, I get 120. And 3 factorial is 6. We've done that one a few times. 120 times 6 is 720. And 320 divided by 720 is 56. So if I have 8 students available to choose from, and I'm choosing them in a way where order doesn't matter, then there are 56 different executive councils I could build out of those 8 people. Now I'd like you to look at the conditions of this particular problem. This was a question where the order doesn't matter and that some of the objects get left behind. I'd like you to think for a minute what a question would look like if you were not leaving objects behind but doing it in a way where order didn't matter. So if I rephrase this then, if I'm not leaving anyone behind, then the feature that I strike out of this paragraph is this. So 8 students are interested in running student council. Okay? If I'm going to take all of them, then that means that 8 students are interested in running for the student council, and I'm choosing 8. And if I'm trying to do a question where order doesn't matter, then those 8 people all have equal positions. So if 8 people showed up, and I'm taking all 8, and the positions don't matter, then I guess I take everyone. And there's only one way to do that. So the way you show that numerically, if you needed to, was I take the 8 people that showed up, I leave none of them behind, and then I eliminate the shufflings of all the people who remain. So 8 objects permuted was 40,320. 0 factorial is 1. Now that's a weird number fact that you maybe have come across. To interpret that, how many arrangements are there of no objects? Well, that's a bit abstract, but so if I give you, just imagine, do it right now, okay? These are literal instructions. Take all of the potatoes sitting in front of you and arrange them in a line. Well, how many ways can you do that? Well, the answer is you stare around your desk saying there aren't any potatoes. Well, that was one way. You got confused. That's the one way to do it. So 0 factorial, arrange no objects, there's one way to do that, which is to refuse. 8 factorial was this number up here already, 40,320. And 1 times 40,320 is 40,320. And any number divided by itself goes in exactly once. Now, if you think about this question, if I changed it to 10 students and I'm taking all of them, the answer would be 1. If it was 1,000 students and I take all of them, the answer would be 1. When this happens, when it's a question that has an answer that you don't really have to think about, the sort of dismissive word used for it in mathematics is trivial. A question where order doesn't matter and you take all of the objects is trivial, unless there's a condition assigned to how you choose people. So when you go through those questions, does the order matter? Am I using all of the objects? Are some of the objects indistinguishable? And are there conditions that I need to meet on the question? It's helping you to find whether you need cases to solve the question. It's also helping you to find out if the question is trivial. So keep that in mind as we go through this. So if I were seeking your feedback at the end of this particular course on a form where you had to rate my performance and the fairness of the tests and the fairness of the exam, etc., 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 but I was only going to sample 3 of the 33 of you, how many different ways could I do that? Well, if you think about course evaluations, I'm going to hand them out randomly to 3 of 33, and then they're going to come back to me, and if I've set them up fairly, they won't have names on them, so it won't matter who hands them in first, because that information is immediately lost. And it ends up being irrelevant in the context of what we're doing, because if my good feedback comes first, followed by 2 bad ones, that's no different than receiving 2 bad ones and then a good one. Net, 2 out of 3 people thought I did a bad job. regardless of what order they handed them in. So this is a question where order doesn't matter. And they're all indistinguishable, right? This form and this form and this form are different forms, so I can tell them apart. The people, in fact, are different, right? Like I can tell all the students apart. So there's no indistinguishable objects. I'm not taking everyone, so I'm only taking 3 out of 33, and there are no conditions on this. So it's that type of problem. So I should be able to do this by taking all 33 people and shuffling them, leaving 30 of those 33 people unshuffled, so I gotta get rid of their order, and then getting rid of the ordering of the people who do receive the form. So if I were to do that using this factorial, I'd have to type in 33 factorial, and if you have a calculator at home, you should do this along with me, because you end up with a number that looks like this. So that number is so large that it had to be rendered in scientific notation. 8.68 something something times 10 to the 36. So just how big is that? Well, if you've taken chemistry, then you've done Avogadro's number, which is the number of molecules in a mole of material. So if you were to take 1 gram of hydrogen, then there are 10 to the 23 molecules of hydrogen inside of that gram. 10 to the 23 isn't this big. I'm off by 10 to the 13. So what I'm asking you to do then is there are 10 to the 11 stars in our galaxy. So if you were to take 1 gram of hydrogen from each star in our galaxy, you would still, what would that be? 10 to the 23 times 10 to the 11 would be 10 to the 34. You would still have to do that 100 times and count the molecules to get a number this big. This is huge. Fortunately, this thing is sitting in the denominator, so let's figure out what that is. 30 factorial is also an obnoxiously large number, 2.652528598 times 10 to the 32. And this little guy down here, 3 times 2 times 1 is 6. Now, my calculator only displayed 9 digits or so. So this number actually continues off screen for quite a ways, right? 32 decimal places, quite a ways. And this one goes on for quite a ways. And we had this nice feature in our counting problems before where I always got a nice round answer, like 8 or 29. You didn't have these horrendous decimals, and if you got a decimal, that was a cue that you had over-reduced the problem. Well, this isn't going to work out real nice. So it would be better if I had a different notation to use. So you can look on your calculator and you can maybe find something that looks like this, or something that looks like this. Either of these are called combinations or choose notation. So in this particular question, I asked the out of 33, the 33 people available, I was going to choose 3. Now, maybe your calculator looks like this. This is the notation that gets used in pencil and paper because it's easiest to write down. In this format, it would be of the 33 people, choose 3. So that's the notation you might see on your calculator. if you can find this button or this button on your machine, take a minute and look. Then you will try typing it in. 33 NCR 3 gives me 5,456. Well, okay. I'm going to try this divided by this divided by this and see what happens. So 8.6833 8.683317,619 times 10 to the 36 divided by 2.652528,598 times 10 to the power 32 is something gross. Divided by 6 is awfully close to 5456. So this notation got me there without having to render any things in scientific notation, which is handy. So if you can find this button, this is a good one to have, especially if we start doing choose problems out of very large numbers. So if you'd like a moment of meta-analysis, which is always really fun, now that we've done the probability distributions unit, you can maybe approach your counting theory in a more structured fashion. So this is a tree diagram of every question where the order doesn't matter. So we already went through that if you take all of the objects in question, so 8 members show up, you choose to take all of the members. If there are no conditions on how you choose them, then this is a trivial question. So you won't be asked one like that because it's a waste of your time. If there is a condition, we're going to have to think about that. So we're going to do a few questions like that in a second. If the order doesn't matter and you only take some of them, and some of those objects are indistinguishable objects, then that's a cases question, which is no different than when we were doing permutations. So anytime you see that you only take some of the objects and some of those objects can't be told apart, you're going to have to use a cases method. And if you find some of those on the practice problems, you're just going to put that star and say, taking some are indistinguishable, write the word cases, put it in a circle, and then leave that question until after you've seen the next video. If the order doesn't matter, you only take some of the questions, or some of them. The order doesn't matter, you only take some of the objects, but those objects can all be told apart, like people showing up for council, and there are no conditions on how to take them. Well, those are the examples we just did. Those are easy ones like 8 factorial, keep the 5 you want, and then get rid of the arrangements of the 3 you leave behind. We haven't done a question like this. So I'm going to erase this tree diagram, now that we've got it up there, and we're going to do an example like this one, where I am taking all the objects, but there's a condition. And an example where there are no indistinguishable objects, and I have to meet some type of condition. So in this particular example, we're taking 15 people and we're putting them into groups of 3. So once I pick them, right, you, and you, then it doesn't matter what order I selected you in, you are now a group. And within that group, you have no rankings or orders, so the order that you end up in that group is irrelevant. Now normally, because you're taking all of the objects, you would just do 15, choose 15, and get 1. That would be a trivial question. But this one has a condition. You're not just grabbing 15 people. As you grab those 15 people, you have to pack them into groups of 3. So this condition rescues this question from triviality. So if we were to go through and give it a try, if you can imagine yourself doing this physically, right, you have to grab the first group. And out of the 15 people in front of you, to make that group, you have to choose 3 of them. And once you've chosen 3 of those 15, there are only 12 people left, from which you have to choose the next group of 3. And then there are only 9 left, from which you have to choose the next group of 3. And then there are only 6 left, from which you have to choose the next group of 3. And finally, we get down to that trivial question. There are only 3 left. How many do you choose? How many ways can you choose that last group? And I mean, in fact, once you've made this choice, this one is predetermined. So the triviality of taking all of the people is preserved in this question, but it got packed down into just this last term. So if you were to think about doing this, in order to take 15 people and split them into groups of 3, you had to do this, and this, and this, and this, and this. Whenever you use that word and, it's implying multiplication. So once I work out these values, I'm going to have to multiply all of them together. So let's set to it. 15, choose 3, is 455. 12, choose 3, is 220. 9, choose 3, is 84. And 6, choose 3, is 20. And of course, 3 choose 3 is 1. So to finish, 1 times 20 times 84 times 220 times 455 is 168,168,000. 168,168,000 different ways you could split 15 people into groups of 3. So here we have 168,168,000 different ways. Now that's an inconceivably large number of ways to sort 15 people into groups of 3, and it turns out to be too big. There's a little detail that we haven't taken into account. So to try and demonstrate that to you, I'm going to take the first 15 letters in the alphabet, A, B, C, D, E, F, G, H, I, J, K, L. 2, 3, 6, 12, 13, 14, 15. Okay. Now, the way I just counted these was I took my 15 people and I chose 3. And then once I chose 3, I chose another 3, and then I chose another 3, and then I chose another 3. So I'm just going to do that here with these letters. I'm going to go D, then E, then F, and then I'm going to choose J, then K, then L. And then I'm going to choose A, then B, then C. Then I'm going to choose M, and N, and O, and then I'm going to choose G, and H, and I. So this is one of the 168,168,000 ways. Now I'm going to do this exercise again. Of my 15 letters, I'm going to choose 3. So I'm going to choose the A, and the B, and the C. And then I'm going to choose 3 of the 12 that are left. So I'll take the M, the N, and the O. And then I need to take 3 of the 9 that remain. So I'll take the D, the E, and the F. Then I need to take 3 of the 6 that remain. So I will take the G, the H, and the I. And then of the 3 letters that are left, which one haven't I taken yet? I'll have to take the J, the K, and the L. So that's also one of the 168,168,000 different ways to do this. But here's where the error lies. If I look at this set of groups here and this set of groups here, they're the same groups. D, E, and F are still together in a group. J, K, L are still together in a group. A, B, C are still together in a group, etc. The only thing I've done here is shuffle the order in which I made those groups. And this question doesn't say anything about ordering. It doesn't say that the first group is more important than the second group, or that the first group has more responsibilities or different tasks to do. They're supposed to be identical groups. So what I've done here is by choosing 3 and 3 and 3 and 3 and 3 is I imposed some order artificially on this counting. And if I do that, I have to remember that to take it back out again when I'm done. So if I look at this, I have 1, 2, 3, 4, 5 groupings here. So 5 groups, and I have to get rid of the order of those groups. So anytime we've gotten rid of order, we've divided by the permutations of those 5 objects. So this number here needs to have a divide by 5 factorial in it. And so does this one. 5 factorial is 120. And so if I grab the calculator, which I don't have on hand, so pause for a second. Let's see, 168,168,000 divided by 120 is 1,401,400 different ways. So to give you an example of a question where the order doesn't matter and you're only taking some of the objects and there is a condition for you to sort, we have the classic sandwich shop question where there are 5 meats available, 6 cheeses available, and 15 vegetables available for your sandwich. How many different sandwiches have 2 meats, 3 cheeses, and 4 vegetables? So the question of order, it seems that every year I get in a fight about this. If you put ham and bacon on a sandwich, that is the same sandwich as if you put bacon and then ham on it. Either way, it goes in your mouth, it gets all mashed up, and then goes in your stomach, all at the same time. So the order in which you put the meats on the bun doesn't really matter. Obviously, we're only taking some of the meats, 2 out of 5, 3 out of 6, and 4 out of 15. The condition is that I'm only grabbing some of these and some of these and some of these. You hear that word "and" again. So I'm going to have to do some multiplication. If you were to physically do this, you would have to choose your meat. And then you'd have to choose your cheese. And then you'd have to choose the vegetables. So, as far as counting goes, there are 5 meats to choose from, and I'm only taking 2. There are 6 cheeses to choose from, and I'm only taking 3. And there are 15 vegetables, and I'm only taking 4. So if I grab the calculator, 5 choose 2 is 10. 6 choose 3 is 20. And 15 choose 4 is 1,365. And since I have to choose my meat and my cheese and my vegetables, I'm going to have to multiply those all together for a grand total of 273,000. So under these conditions, for this particular question, there are 273,000 different sandwiches you could make that have 2 of the 5 meats, 3 of the 6 cheeses, and 4 of the 15 vegetables. So suppose you have a stapler, teacup, your laptop computer, the butter dish, and a cat sitting on your kitchen table, and you're off to your friend's house, and you're trying to decide how many different ways you could shove those objects into your backpack and carry them there. So the reason I say backpack is we're trying to do questions where order doesn't matter. So if you shoved the butter dish, the teacup, the cat, and the laptop into the backpack and then hoisted them over your shoulder and then ran your way to your friend's house, by the time you get there, the order in which you put the objects in is irrelevant. I mean, the laptop will probably be broken, as will the teacup, and the cat will be angry. So, and it doesn't matter if the cat went in first or last; it still probably peed on the floor when you let it out. So, the order doesn't matter. The question is a little ambiguous because it said some of the objects. So, I might take none of them, right? I might look at the cat hissing loudly near my very expensive laptop computer, and I might say this is a poor choice, so I'm going to take none of them. Or maybe out of those 5 objects you only take 1. Or maybe out of those 5 objects you only choose 2 to take. Or maybe out of those 5 objects you only choose 3. Or maybe you only choose 4, or maybe you choose to take them all. So those are your options. So if you have 5 objects on the table and you choose to take none, that's the trivial question there, right? You choose to take nothing out of the 5. So how many ways can you do that? Well, you look at the assortment of random things on your table and say, this is a poor choice, and you just walk away. Well, that's the one way you can do it, right? You refuse to participate in the exercise. On the other end of the spectrum is another trivial question. With the 5 objects on the table, how many ways can you shove all of them in the backpack? Well, 1. You give them the big arm sweep, in they go. Over here, if you have 5 objects in front of you and you're trying to choose just one of them, well, you could pick either the stapler, the teacup, the butter dish, the cat, or the laptop computer. Only one of those, and there are 5 different objects to choose from. So this is going to be 5. On the other end of the spectrum, if you shove 4 of those objects into your bag, then you have selected one object to leave behind. So if you sort of stew on that for a second, choosing one to take should be the same number as choosing one to leave. So taking 4 objects there should be 5 different ways to do that. As for this one, I can do this the old-fashioned way, 5 factorial, shuffle them all, eliminate the shufflings of the ones I leave behind, and eliminate the shufflings of the ones I take. I could do that here as well. Leave 2, take 3. Do you notice that these 2 fractions will be the same? 5 factorial is 120. 3 factorial is 6. 2 factorial is 2. This one would be 120 over 2 times 6. This ends up being 120 out of 12, which is 10, as does this one. So there's a symmetry in this arrangement if I'm lining up all the different ways I can take some of the object. So I'm just going to park those numbers in, 10 here and 10 here. And then I'm going to erase this stuff on the bottom so it's not distracting. I want you to take a look at that row of numbers that I just put up there. 1, 5, 10, 10, 5, 1. Familiar? Well, it should be, because if I were to just quick build a Pascal's triangle for you, 3, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. There it is, right in the 5th row, I guess it's the 6th row, of that Pascal's triangle, those numbers, 1, 5, 10, 10, 5, 1. So when you were doing your binomial distributions, and you were following pathways to get to the end of a tree diagram, and if you were doing a question like the "May the fours be with you" question, where you were really only hunting for fours, and you needed to know which pathways you arrived at, if I told you that 2 out of 4 dice rolls turned up the number you wanted, well, that means that out of the 4 dice that you threw, you have to choose 2 of those branches to hold the number you were after. So it could have been the 1st and the 2nd, it could have been the 1st and the 3rd, it could have been the 1st and the 4th, it could have been the 2nd and the 3rd, it could have been the 2nd and the 4th, it could have been the 3rd and the 4th. That added up to 6 different ways to do it. So when you were doing your binomial distributions, these Pascal numbers showed up because you were doing the combinations of dice rolls or whatever that would end up at the end of the branch you were after. So the last thing I want to say about this is your NCR notation, right? We already covered that. And then this little arrangement generates Pascal's triangle. And if you're looking to check to make sure that your Pascal's triangle rows or that your combinations are correct, I just want to point out one little thing. If you add up 1 plus 5, you get 6, plus 10 is 16, plus 10 is 26, plus 5 is 31, plus 1 is 32. If I did this row, 1 plus 4 is 5, plus 6 is 11, plus 4 is 15, plus 1 is 16. 1 and 3 is 4, plus 3 is 7, plus 1 is 8. 1, 2, 1 would be 4, 1 and 1 would be 2, and 1 is just 1. Now that's a funny set of numbers, 1, 2, 4, 8, 16, 32. Do you notice that they double as they go down? Do you notice also that this is 2 to the 0, 2 to the 1, 2 squared, 2 cubed, 2 to the power 4, 2 to the power 5? Well, this particular question here, if you were to go through these objects, you looked at the stapler and you either said yes or no. So you made a tree diagram that branched yes or no at the stapler. And then you looked at the teacup and said yes or no. So you had a branch, 2 branches come off of that one. And then you looked at the cat and you said yes or no, etc., 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 for all 5 of these objects. So you did a tree diagram that had 5 choices, and at each of those 5 choices there were 2 levels. So 2 choices for the stapler. At the end of each of those, 2 choices for the teacup. That's 4. At the end of each of those branches, 2 choices for the cat. That's 8. You see how it's growing that way? So when you're making these choices of things and doing a combinations type question, you may be able to reduce the problem into, do I take this or do I not take this? And you may be able to render the thing as a power of 2, depending on how many of these cases you're allowed to collect.